Uh, Welcome everyone. I'm Soikat. I'm a final year PhD student at ICTS. Uh, so I first thank the organizer for giving me this opportunity to talk about our work here. So the title of the slide is changed slightly. Today I'm going to talk about tracer dynamics in single file motion in presence of activity. So this work is done in collaboration with Anupam and Prashant. Prashant was a PhD student here. Now he's in Niels Bohr Institute, Copenhagen. Okay, so let me start with the definition of single file motion. Okay, so the motion of particles in narrow channels where the particles cannot overtake each other is referred to as single file motion. So that is shown schematically also, the channel is denoted by two horizontal blue lines and the particles are inside it. The motion of the particles are such that they can't overtake each other. So that is actually known as single file motion. Now, where do we see this kind of motion? So that you can see like the non-overtaking vehicles in this lane that can be thought of this single file motion. So here they don't have space to overtake. So as a result, the ordering of the vehicles remain intact. We can see this in other scenario also, like in non-overtaking crowd in queue. So here you can see like the space is there, but you shouldn't overtake any other people. Okay, now due to this non-overtaking constant, the physics changes quite drastically. So you don't only get quantitative changes, you get some qualitative changes as well. So that can be understood from this figure. So here I've plotted trajectories of 5 independent Brownian particles. So here you can see like the crossing is allowed. Okay, so if you see this, let's say the green trajectory, so here you can see that it is actually crossing the other colors also. So as a result, if you compute the mean square displacement of this particle denoted by this green trajectory, then it is actually diffusive in time, like proportional to time. But if you consider the following scenario, where the crossing is not allowed, let's say this green trajectory, so you can see like it is always in between this blue one and the brown one. So in this case, if you compute the mean square displacement, it is actually becomes subdiffusive and it grows square root as square root t. Okay, now this coefficient that here like this zeta one, xi1, that is actually computed in many other passive particle systems in single file motion, and it depends on the initial density, interaction among the particles, and other parameters also. Now we ask what happens to this coefficient in presence of activity. And there are several numerical studies which confirm that the coefficient associated with this temporal growth gets non-trivially modified, but there is no expression like the theoretical form of this xi1. So with that motivation, we started this project, and we considered this active random average process model. This is actually the active version of the well-known random average process model. So let me tell you the model. So that is actually shown in schematically. So here the particles are on a one-dimensional line, and the solid circles denote the position of the particle at that instant. The arrows denote the velocity direction of that particle. So let's say it is in the right direction, then the velocity is positive and the spin of the particle is 1. And if it is in the left direction, then it is like the spin of the particle is -1. So if we know the position of the particles at any instant time t, then at any later instant t plus dt, the position of the particles will be given by this evolution rule as it is in equation 1. Now this increment that is actually written here. So if the spin of the particles is +1, then the first part, the term inside this bracket is 1, and with p dt probability, it jumps to its right. Like this is the space available to it at xi plus 1 minus xi of this particle, and eta is some fraction in between 0 to 1. Okay, so it can't cross. Okay, so with this amount, it can jump to its right, and if the spin of the particle is -1, then the first term is 0, and this term is 1, and with p dt probability, it jumps to its left, and with the rest of the probability, it stays there. Okay, so this is the model we are considering. Now we look at the results. So as I mentioned, like we wanted to compute this mean square displacement, and here what we have found that the mean square displacement changes from diffusive to subdiffusive, like diffusive at small time and subdiffusive at later time, and we computed this coefficient xi1 explicitly, and that is written in equation 3. So you can see these terms like Ci, Ti, and C1 that is actually denoted by different colors. So these are the terms which arise due to this activity, and the terms here, it is actually the original, the term which already obtained in the original random number process model, and these are the terms due to this activity. So and Ci and Ti is written here like Ci as the 2-point correlation function like Z0 sigma I, and Ti is a combination of 3-point correlation function like Z0 Zi plus 1 and sigma I. One thing to mention here is that like we wanted to compute the mean square distribution that is like just 2-point correlation function, but here for that we need the information of 3-point correlation function. So this is the feature of activity here. Like if we want to compute the 2-point correlation function, we need the information from 3-point correlation function. If we want to compute 3-point correlation function, we need 4-point correlation function and so on. So that hierarchy is there in this active systems. Okay, now we compare it with numerical simulation. So here I have shown like the mean square displacement as a function of time, and the points denote the numerical results, and these blue lines denote the theoretical form, and MRAP denotes the corresponding original random average process model. There is no activity in it, like this is for passive systems. Okay, that you can see like it is matching quite well, and with increasing gamma, that is actually the flipping rate from sigma equal to +1 to -1 and vice versa. So here with increasing gamma, and it is approaching towards the MRAP model, and we expect like the gamma tends to infinity, they will match exactly. We also computed the correlation functions, like computed two particle correlation, and it has a scaling function structure like GIT is G0T times some scaling function, and that is written here. And this scaling function, which is already obtained in the original random average process model in this reference, but one difference we are getting like only in this coefficient Xi1. The scaling function, everything remains same. Okay, so as a conclusion, like we explicitly find this coefficient Xi1, and here what we find that which requires information from higher point correlations. The temporal behavior as well as the scaling function all remain same as in the original random average process model. The difference appears only in this coefficient Xi1. And this is the prepend. Thank you.
We can have a couple of questions.
Temperature of the bath. Physically, how you can realize the system? I mean that this coefficient, is it related to the effective temperature of the medium?
That you can think about, yes. Like higher the activity, higher the temperature is affected.
Okay. Have you looked at the initial condition dependence and the p-factor of square root 2 dependence?
Yes. Yeah, that I have not presented here. Like we have computed the autocorrelation function also, and there is this exact.
Even in the active regime where it becomes diffusive, do you still get a square root of 2?
Yeah, even in the higher activity regime, it is square root 2.
Thanks.
In your model, where did you take the fact that it cannot jump, it cannot overtake? That is not in your model, right? That one that you presented.
It is there. Here you can see like eta I is some random number in between 0 and 1, and this is the distance which is available to this particle in the right direction. So it can't jump by this amount, like higher that amount.
Let's check one second.